Hi, my name's Sean. I'm the founder of a company called Renderlet. Today we're going to talk a little bit about how we are using WasM specifically for GPUs in order to help build magical content for your interactive applications. Just a bit of a background. What is Renderlet? Renderlet is a safe and portable rendering framework that can be embedded into apps. So you might be familiar with things like Unity, which is more of a game engine, or even things like WGPU, if there's any Rust people in the crowd, kind of a low-level rendering library. We roll in the same circles, but Renderlet is kind of a different way of doing this, where we take the entire engine, all the surrounding code around it, we compile it to WebAssembly modules, and you get this nice, portable, safe WebAssembly-based abstraction for your graphics that just kind of runs anywhere. What do I mean by magic content? I think we can much more quickly than we do today build content for interactive applications. Things like shading effects, rendering plugins, maybe games, maybe browser-based games, or even embedding content into existing video games. Taking that content, and let's say you've got a CAD file, you want to be able to interact with the CAD file inside a different application or inside a document. Being able to distribute your GPU compute, so being able to take the same binary and at runtime, being able to make a decision on, do I run this on device, do I run this maybe remotely and stream the output back? Or even today, what we're going to be talking about, which is a little less exciting than that, but still very cool, procedural generation. So, who here has worked with Adobe Flash before? I know, yeah, okay, good, most of the crowd. I know I'm not dating myself too much. On Hacker News, Renderlet has been compared to Flash. I don't know how I feel about that, but here's what I say to that. Anybody remember some of the issues with Flash, other than, and I used to work at Adobe for many years, so Flash is a great product. It was kind of the dawn of the internet, bringing interactive content into a browser and even into desktop applications. But what it's probably most recently, most famously known for is security vulnerabilities. Has anybody ever had to program against a Flash DOM before, like extracting text fields out or something? Yeah, okay, we got two hands back there. Not fun, is it? It's not designed to be extensible. Can't directly use GPU compute inside something like that. Obviously, like vector rendering backends these days can be rendered in compute shaders, but you don't have access to anything like that to guess code. And also, remember the little pop-up of it's time to update Flash Player? Yeah, we're not going to do any of that anymore. So we are secure via WebAssembly. We have automatic data bindings into DOM trees and property trees and render trees for games or other interactive applications. We're able to safely expose web GPU functions and like GPU sandboxes to apps so they can run GPU compute. And everything is batteries included inside their own WebAssembly modules. Brief overview of how we do this. I'm glossing over a lot of technical detail here, so I apologize. But you can think of different Renderlet objects like components. I say component lightly. I do not necessarily mean WebAssembly component model components. We do use the component model for some things. We use core WasM modules for other things. That's fine. But we build a data interface between these different modules, and we call these GPU component interfaces. And we allow these to talk to each other in order to build a render graph. And so a host application will expose its GPU API to a Renderlet application. And the app will call through our SDK and run the WebAssembly payloads. And it just kind of automatically ends up in the GPU, shaded onto the canvas. Some of the backing structures behind this, we're heavy users of WGPU. You can view these like low-level objects if you have a graphics programmer in here. Buffers, shaders, all of these low-level bits, we generate most of these for you. We do expose, we'll talk about this later, we do expose the web GPU API so you can also write some of these yourself. But an important distinction is we can run in the browser, we can run outside of the browser, we can really run just about anywhere that right now you can run wasmtime and WGPU if you're outside of that. We're building a project called WASI Web GPU, which hopefully as of tomorrow morning will be a phase 2 WASI proposal. And this allows us to expose the web GPU API to WebAssembly running outside of a browser. So we can take that same binary and we can just kind of run it anywhere. And then last thing to note is, mentioned a lot about web GPU. Web GPU is not perfect. Obviously there are native graphics APIs behind this. Here's some of the popular ones. There's some very interesting things in procedural generation that are reliant on things that are not necessarily in WebGPU. They'll probably come to WebGPU someday, but there are ways we can expose similar interfaces outside of, through interop, outside of WGPU to guest apps so they can do some of these interesting things today on native hardware, not in a browser. Okay, enough of that. So I love this image. This is from a talk by Andrew Price called The Next Leap, How AI Will Change the 3D Industry. So this is a scene from Tom Clancy video game. I forget the name of it. I don't have my speaker notes right now. But this is kind of the estimated cost to build all of the objects in this scene. An estimated rate of about $60 per hour for a 3D artist to actually sit down and build this kind of content. You can see the prices add up very quickly. Why is this? Anybody have any guesses? I don't want to just stand here. Interactive. Say something. Why is building content so hard?
You have to do it all from scratch.
You have to do it all from scratch. Exactly. Thank you, Paul. You have a 3D artist who's maybe hand poking around polygons, being able to tweak things, being able to take off-the-shelf assets, adapt them to work in an engine. You don't see a whole lot of generative AI. You don't see a whole lot of these different automated techniques making their way in mass. To be clear, there's some wonderful systems for games, but in mass taking over the industry yet. So this photorealistic-ish scene of Manhattan here has become very expensive to develop very quickly. Why? Well, let's talk about how objects are represented in 3D space. They're typically designed with a tool. That tool has some sort of mental or object model. I'll use the example of a table. So this table has semantics. If you are designing in your head a table, it probably has a top. It probably has sides. It probably has legs. So this is what we call a semantic model of an object. And often in modeling tools, that is the same kind of mental model you're working with. But that is what I will define as a continuous representation of an object that's very often converted to polygons at design time. It's exported. So you're generating a GLTF or something, and you're exporting that, and then you're importing that in, and so it looks something like that. Just a wireframe view of that. So all of a sudden, we've lost all that semantic information. We just now, it's renderable. We can shade it in our engine, but it's not something that you can go back to and say, like, I want to change the dimensions of these legs, for example. Okay, so demo time. We're going to go over to a couple of apps that use WasM for content creation right now. If my internet is working. Yes, perfect, first. Okay, this is something called Project Neo from Adobe. If you haven't checked this out, check this out. It's a very cool app. It's an SDF-based modeling tool that runs in a browser based off of WebGL. You can interact with these little objects, and you can build these really cool volumetric animations out of a series of effectively linear functions. A challenge is if I wanted to render this inside my own application, if I want to take this model and take this model's data and render it, I couldn't necessarily do that directly. My download options are as a ping or as an MP4. And when we talk about SDFs, we talk about why. But you can see there's already kind of a export flow coming out of this tool where we're not able to necessarily run that content in engine. A little bit more relevant to our example, I'm going to go over here to, this is from S3, this is called ArcGIS Urban. And so this is a building model, I think this is of Boston, Massachusetts. You can see here, we can even go, see if the internet can catch up. Like I can zoom in, I've got hierarchical level of detail. I can see these models of these buildings, and I can, let's see, lost my options. But how do I change these objects? How am I able to take these, which right now are just exported to vertices and meshes, and how do I actually generate this data ourselves and keep that at design time and runtime itself? So we've kind of established WasM's cool for being able to, I think Paul mentioned this in his newsletter a couple months ago, the WasM engine architecture, where I've got maybe a JavaScript app, it's talking about backend that's in WasM, it's putting data on the GPU, but we're still stuck by our current export formats. So this is why. This is how this often goes. Let's say I am a designer and I am trying to make an animated disco ball. I've got our friendly little game developer over here who is, they're both very happy, right? And so they need to be able to build that out of a sphere, and the game dev says, cool, we've got some geometry functions, here you go. And they're gonna try to figure out how to work with that in their content creation tool. I need data to animate this. Let's say we are doing a fast Fourier transform on the music that's being played to modulate the lights that are on this disco ball. Well, we've got to add all those parameters and carry them across and map them to shaders and figure out how to work with that inside our DCC. And then it looks weird. And you can see the look of consternation on everybody's face now. Why does it look weird? Well, I don't know. I guess that here's a shader from the engine, and we're going to try to make this work in the content tool. And I don't know. You see, there's a lot of back and forth. There's a lot of ping pong on this. Here's how this should work. And this is where tools like procedural modeling can come in and help. You've got a library. You've got something that has defined functions that say, here's a defined set of inputs. Here's how we're able to build a model that works for all of these different use cases. Using something like Renderlet, where we can expose GPU components, you can take that, you can parameterize it, you can plug it in the engine, you can automatically shade it, and you got your disco ball. Everybody's still happy. So and I'll actually go back. I wanted to find something. So this is design time procedural modeling. So there's a set of shape grammars. There's a set of things that run that generate the polygons that are here in this app. You have a set of rules that say, here's the footprint of a building, and I want to extrude it. But what we want to do now is we want to take that, and we want to run the procedural modeling at runtime. We want to be able to generate graphics data through code. We want to be able to not export those as a polygon mesh. We want to be able to run our entire procedural pipeline in real time, very quickly at runtime. I think quickly is one of the reasons why I haven't seen as many of these techniques take off over the years, because there's not a high performance export path that can run at 60 frames per second. And we want to be able to keep those semantics that we talked about. We want a table to still be a table. We want a building to still be a building. Okay, quick overview on different types of procedural models. First, we'll look at L-systems, Lindenmayer systems. So this is a parallel rewriting system for tree structures. If you want to generate something that looks kind of like that. That is literally a tree. This is a rewrite tool. A grammar for that would look something like that. We're defining how the branches split off based off of probabilities and error budgets. And it's effectively a parallel recursive algorithm that allows those branching structures to progress if you were to imagine that tree growing in parallel over time. Sign distance fields or sign distance functions are another procedural technique, very different from that. This is where we represent our objects kind of as the intersection of volumes. This is a broader definition than some might say, but an intersection of volumes defined by functions. And here, I've got this little guy. This is an image from Project Neo, but if anybody here has anybody here ever used Shader Toy? Okay, we've got a few hands. So this is from Inigo Kiaz. He's the author of Shader Toy and Project Neo. Cute little guy that's made of blobs. And here's what the code for that might look like. And so here you've got effectively different functions that are defining a continuous shape. And the challenge with this is you can't really export these polygons, or at least animated polygons, very easily. And that's why, if we were taking it back to that demo, why maybe we export it as a video instead, because we probably have to ray-march this in runtime. Okay, let's talk about another, split grammars. So that is a recursive parallel formula that allows us to partition dimensions around aligned axes. So it's somewhat similar to an L system, somewhat not. Here's a great example of this. This is my shower. These are the tiles in my bathroom. What is a mathematical formula that could represent how these tiles are laid out if we're trying to generatively build a texture of this? Here's a model that we use in Renderlet. It's kind of a DSL for that, where we say, okay, cool. We're going to split that along the y-axis by proportion dimensions. We're going to split that relative to the height so it can repeat and then scale to the height of the overall object. So if you're to drag and drop the height or the width of the shower in real time, you can see it scale to that. Can't forget the grout. Can't just have tiles. And we're going to do the same thing in the x-axis, and then we're just going to sample, let's say for the grout, we're going to sample a concavity function, and for the kind of modeled texture on the tiles, sample some Perlin noise. And we will do that, and you see a little caret there, we will do that relative to the size of the overall object, not the size of each individual tile, because otherwise, each individual tile would look exactly the same, but if you look at the pattern, it's kind of randomized across the entire wall. Okay, and then our last example here is shape grammars. So this is kind of split grammars on steroids. We extend split grammars to generative geometry operations. And so that's when you think back to the example from ArcGIS. That's how you can build scenes like this. This is a language called CGA. This is just some example code from that. And so this is how you define a split like that, but you'd also define things like extrusions and geometry operations as well. And that's how you generatively build a model of a building that looks kind of like that. Okay, so let's get our hands dirty. Here's what that might look like using Renderlet. Here, I've preloaded a lot of this just for the sake of time. Here we've got a grammar that is defined in a Renderlet render spec that says, I want to build a building that looks like this, which is kind of not a whole lot right now. But let me walk you through this. We've got a start rule. If you imagine this, this is a rectangle that we have then taken that 2D plane, extruded it to a height, and then colored the sides and the top of it. So we're going to start by parameterizing this. We were going to say like our depth is 8 meters, our height is 18 meters, for example. We're going to then size that polygon to fit that. Starting polygon's a rectangle. We're going to extrude it by that height. So that's going to grow it from a 2D to a 3D shape. We're going to split that into its components. And then we're going to color those different components. The top and the wall are a different color here. So that is a generative procedural model for a very ugly block that is not really a building. Let's go over here. Okay, so whoa, this is white. Why is that? Well, I want to actually show an example here for real. So here we have a start rule. We're doing the exact same things we did before. We're splitting this into its components. But then we're performing some operations on top. I won't explain them too much, but you see we get that nice little shape up there. And so we're going to do offsets. We're going to, like, let's say, move the polygon in or out or up or down in order to build that lead shape you see at the top. Why are our sides white? Well, that's because if you look at the component split operation, we have side, and our sides defined by a facade rule, and I don't see a facade rule in here. But I think what we meant to do was that. So now I'm going to recompile this. This is going to, we have a real-time version of this that is broken right now, so apologies. So I just had to run that entire, but I messed something else up too. Apologies. Talk-driven development. I want the side to go to wall. This can work in real time. Right now we're actually generating an entire C++ module on the back end, compiling it to WebAssembly, linking in all of our code. This is like the export version, but you can see it's still pretty fast. Okay, cool, so now it's not white. Now we have a brown building. Now, what if we want to enhance that to actually look like a building? We're going to go over here to this third grammar, and there we actually have a building. And so what did we change? We added another function. You remember that dangling facade function? We added a new grammar to this with a facade function in it. And here we've implemented component splits, and we can do this in parallel. And if you think back to split grammars, here we can say, okay, we want to split in our x-axis by this amount. We want to split in our y-axis by this amount. We want to be able to reason about the size of these shapes and run all those calculations parallel to generate an object that looks like this. So cool, okay. We have something that reasonably resembles a building now. Here's how that kind of works. I covered already that we compile that all to WASM. Can actually, here, oops, actually show you. This, whoa, not working? Okay, cool. This is an example of what that might look like. You see we're auto-generating all this C++ code. We've taken all those parameters. We've built this set of libraries. We're linking into the WASM module. And it's generated C++, but this is just code that executes to generate that building. Okay, cool. And so a host app would use the Renderlet SDK, pass in format and instance data. The WASM sandbox will run all that generated code, and it will spit out onto the GPU directly by mapping this into WASM linear memory, the objects that are necessary to render it, the buffers and the vertex buffers and the shaders, et cetera. We attach to a render target, and then we draw. So that all the app has to do is, through a little interface, give access to its back buffer, and give access to the code to effectively render that WASM safely onto its canvas. Okay, so I showed you the design time. Now let's see that at runtime. I have a sample app here. is paused. I'm going to take the output of that last compile here. I already have it saved. I'm going to resume that. Here's a map viewer. This is based off of Bing Maps. You can see here is an area just south of here. I think this is around San Jose. And so we're going to, boom, there we go. Okay, so now we've got these buildings. You see they look a lot like what was on the screen there, but we have a bunch of them. We have a grid of them. They're all somewhat different in color, and in size and in shape. So how do we do that? Well, if you go back to this, we added the ability here in this fourth one. Oh, I had recolored that. We added the ability here to export or hook up exports from this WebAssembly module. So now we've got these parameters that the host app is passing in based off of instance data that is able to control the colors and the sizes and the shapes and show all of these at the same time. And so the last point I'll show here, I gotta hold this. See if I can do that. That's kind of awkward. Okay, so we've implemented like real-time atmospheric scattering in here. Cool, it's a map, it gets dark at night. Wouldn't it be cool if those buildings lit up at night? Well, we can do that. I'm a little pressed for time here, but I will show you here this function we've implemented that effectively modulates with some random parameters an output color. And so we're generating this function in the WASM module. Through our SDK, we can automatically hook it up to instance data that's being rendered in the shader. And then if I go back here and load that module. Whoa, cool. Okay, so now we can, based off the angle of the sun and some other parameters, control the lighting of those buildings. So we didn't write any code in this app to do this. This is all part of the Renderlet module, and we're able to hook that up to the shader itself. Okay, that's it. With Renderlet, we use WASM heavily. You can build interactive content faster. We want to take things that happen in design tools today and bring that to runtime and vice versa, so we can keep things in sync and build better content. Come find me after if you want to chat more. We are always hiring GPU experts. Thank you.
Thank you, Sean.